Albert Einstein, a name synonymous with genius, reshaped our understanding of the universe. His contributions to science are unparalleled, and his theories have stood the test of time, continuing to influence modern physics and cosmology. Born in Germany in 1879, Einstein's inquisitive mind led him to question the very fabric of reality. From a young age, he was fascinated by the mysteries of the natural world, often pondering deep questions that others took for granted. His groundbreaking theories of relativity, both special and general, revolutionized physics and continue to shape our understanding of the cosmos. These theories provided a new framework for understanding the relationship between space, time, and gravity. Before Einstein, physicists viewed space and time as fixed and absolute. The prevailing view was that the universe operated like a well-oiled machine, with predictable laws governing the motion of objects. Newton's laws of motion reigned supreme, describing a universe where objects moved in predictable ways. These laws had been the cornerstone of physics for over 2 centuries, providing a solid foundation for understanding the physical world. But Einstein envisioned a more elegant, interconnected universe. He proposed that space and time were not separate entities, but were intertwined in a 4-dimensional fabric known as space-time. His theories challenged conventional wisdom and opened up new vistas of scientific exploration. They paved the way for numerous scientific breakthroughs, from the development of GPS technology to the discovery of black holes. Einstein's genius lay not only in his profound insights, but also in his ability to communicate complex ideas in simple terms. He had a unique talent for making the abstract concepts of relativity accessible to both scientists and the general public. He used thought experiments, often involving trains and flashes of light, to illustrate the counterintuitive nature of his theories. These imaginative scenarios helped people grasp the strange and fascinating implications of his work. These thought experiments, while seemingly simple, held profound implications for our understanding of space, time, and gravity. They revealed the relative nature of time and the warping of space-time by massive objects. In the following sections, we will delve into the fascinating world of Einstein's relativity, exploring the mind-bending concepts of time dilation, length contraction, and the curvature of space-time. These phenomena have been confirmed by numerous experiments and observations, solidifying Einstein's legacy as one of the greatest minds in history. We will journey to the edge of black holes, where gravity reigns supreme, and explore the ripples in space-time known as gravitational waves. These cosmic phenomena provide a window into the most extreme environments in the universe. Join me as we embark on this cosmic adventure, guided by the light of Einstein's genius. Together, we will uncover the secrets of the universe and gain a deeper appreciation for the remarkable mind that forever changed our understanding of reality. In 1905, a young patent clerk in Bern, Switzerland, published a paper that would change the course of science. Albert Einstein, at the age of 26, unveiled his theory of special relativity. This groundbreaking theory challenged the very foundations of physics, overturning centuries of established thought. Special relativity emerged from Einstein's fascination with light. He was captivated by the fact that light always travels at the same speed, regardless of the observer's motion. This seemingly simple observation led him to a profound realization. The speed of light is constant, and it is the fundamental speed limit of the universe. This realization had profound implications for our understanding of space and time. If the speed of light is constant, then our measurements of space and time must be relative. This means that observers moving at different speeds will measure time and distance differently. Imagine 2 observers, one standing still and the other on a moving train. Both observers measure the speed of a beam of light. According to classical physics, the observer on the train should measure a different speed of light than the stationary observer. However, Einstein's theory predicts that both observers will measure the same speed of light. The constancy of the speed of light is one of the most mind-boggling concepts in physics. It challenges our understanding of the universe and forces us to rethink the very nature of reality. It defies our everyday intuition, where speeds seem relative to our own motion. In our daily lives, we are accustomed to the idea that the speed of an object depends on the observer's frame of reference. For instance, if you throw a ball forward on a moving train, it appears to move faster to someone standing on the ground. This is because the speed of the ball is added to the speed of the train. However, light does not behave this way. Unlike the ball, the speed of light remains constant regardless of the motion of the source or the observer. Imagine a beam of light traveling from a flashlight to a mirror and back. This simple experiment reveals the unique nature of light's speed. Now imagine that same experiment taking place on a spaceship, moving at a significant fraction of the speed of light. The scenario becomes even more intriguing. You might think that the light beam would have to travel farther on the moving spaceship, and therefore take longer to complete the round trip. This seems logical based on our everyday experiences. However, this is not the case. The speed of light remains constant, and the distance it travels does not change even on a moving spaceship. Both an observer on the spaceship and an observer on Earth would measure the speed of light to be exactly the same. This consistency is a cornerstone of modern physics. This is because time itself slows down on the moving spaceship relative to the observer on Earth. The phenomenon of time dilation ensures that the speed of light remains constant. This phenomenon, known as time dilation, is one of the most bizarre and counterintuitive predictions of special relativity. It shows how intertwined time and space are. The constancy of the speed of light has profound implications for our understanding of the universe. It affects everything from the behavior of particles to the structure of space-time itself. It means that there is no absolute frame of reference, no single point from which we can measure all motion. Every observer, regardless of their state of motion, will measure the speed of light to be the same. All motion is relative, and the laws of physics are the same for all observers in uniform motion. This principle is fundamental to our understanding of the universe and underpins the theory of relativity. The constancy of light speed also leads to fascinating phenomena such as gravitational lensing, where light bends around massive objects, revealing the curvature of spacetime. Even the light from distant stars can be bent by the gravity of black holes, showing us the incredible power of gravity and the unchanging speed of light. Understanding the constant speed of light helps us grasp the vastness of the cosmos and the expansion of the universe. It is a key to unlocking the mysteries of space and time. Section 4. Time is not absolute, time dilation. Time, once considered an unwavering constant, was revealed by Einstein to be relative. This groundbreaking revelation fundamentally changed our understanding of the universe. Time dilation, a consequence of special relativity, dictates that time is not experienced equally for everyone. This means that the passage of time can vary depending on the speed at which an observer is moving. It hinges on the observer's relative motion. The faster an object moves, the more pronounced the effects of time dilation become. The faster you move through space, the slower time passes for you relative to someone who is stationary. This effect, although imperceptible at everyday speeds, becomes significant at velocities approaching the speed of light. This concept, though seemingly bizarre, has been experimentally verified. Scientists have conducted numerous experiments to test and confirm the predictions of time dilation. Atomic clocks, incredibly precise timekeepers, have been flown on airplanes at high speeds. These experiments are crucial because atomic clocks can measure time with extraordinary accuracy, down to billionths of a second. Upon their return, these clocks showed a minuscule but measurable time difference compared to their Earth-bound counterparts. This tiny discrepancy is a direct result of time dilation. The faster-moving clocks had indeed ticked slightly slower, just as Einstein predicted. This experimental evidence provides a tangible demonstration of the theory of relativity. Imagine a pair of twins, one remaining on Earth while the other embarks on a high-speed space voyage. This thought experiment, known as the twin paradox, illustrates the effects of time dilation in a more relatable way. Upon the traveling twins' return, they would find their Earth-bound siblings significantly older. This dramatic difference in aging is a direct consequence of the time dilation experienced by the traveling twin. The traveling twin, having moved at a significant fraction of the speed of light, would have aged less due to time dilation. This scenario, while hypothetical, underscores the profound impact of relative motion on the passage of time. This is often referred to as the twin paradox, though it is not a paradox at all, but a fascinating consequence of special relativity. The term paradox arises because the outcome seems counterintuitive, yet it is entirely consistent with the principles of relativity. The effects of time dilation become more pronounced as we approach the speed of light. At these extreme velocities, time can slow down to a crawl, making the journey through space a journey through time as well. While the time differences we experience in our daily lives are negligible, they become increasingly significant at speeds approaching the cosmic speed limit. Understanding time dilation not only deepens our grasp of the universe, but also opens up possibilities for future space travel and exploration. Section 5. Length contraction. Objects in motion shrink. Another intriguing consequence of special relativity is length contraction. This principle states that objects moving at high speeds appear shorter in the direction of their motion relative to a stationary observer. Like time dilation, length contraction becomes more pronounced as the object's speed approaches the speed of light. To visualize this, imagine a spaceship traveling at a significant fraction of the speed of light. An observer on Earth would measure the length of the spaceship to be shorter than its actual length, as measured by an observer on board the spaceship. The faster the spaceship travels, the more pronounced the length contraction. This phenomenon is not an optical illusion. It arises from the fact that the very fabric of space-time is warped at high speeds. Just as time is relative, so too is distance, and both are intertwined in the fabric of space-time. Length contraction, like time dilation, has been experimentally verified. Particle accelerators which propel subatomic particles to near light speeds observe length contraction in the particles they accelerate. These experiments provide further evidence for the validity of Einstein's revolutionary theory.